So this is my research work presentation. I am proposing this pragmatic algorithm of a resumptive inline Pori model. The proposed Pori model is forming a machine cell and part family clusters in two stages. In first stage, a similarity coefficient algorithm is forming machine cells part families. The second stage, as resumption, the same clusters are iterated by the weight-based method to get proper partitioning. As novelty, incorporating job sequence weight ratio, setup, handling time, and waiting time in manufacturing time ratio, the ratio of present and new batch sizes, which are having a significant impact in finding complete similarity for machines as well as components. The authors uniquely incorporate necessary manufacturing data such as alternative process plans, job sequences to improve the similarity coefficient. The assumptions in the Pori algorithm as well as optimization model are the manufacturing time is considered as double the values of setup time, processing time, as well as handling time. The current demand, future demand, as well as batch sizes are known for fixed periodic intervals, and number of batches are also calculated. The purchase price and duplication budget are known for all the machine types. Subcontract price, intra-cell and intra-cell movement cost are known for all the parts. The entire demand has to be completed in the manufacturing within the time period. The machines to be duplicated, parts to be subcontracted, inter and intra movements are taken as decision variables. So algorithm consisting of like these 10 steps. So in the first step, we are starting by preparing the input data with the machine part incidence matrix. So in the second step, we are computing a similarity coefficient for machines as well as parts using equations 3.12 and 3.13. So in the step 3, we are computing weights for rows and columns. And in step 4, we are sorting descending order of weights in rows and then columns. The step 5, we are doing iteration again and again of steps 2 and 3 in the spreadsheet simulation until there is no change in the order of rows as well as columns in the matrices. Now in the step 6, we are identifying the machine cells as well as part families. So in the step 7, by doing weight based method, we are once again refining the part families as well as machine cells. First number of part and then and then machines. If number of parts are more than the number of machines. The step 8, we are computing weights for parts as well as machines with respect to machine cells as well as part families using equations 3.3 and 3.4. So in the step 9, we are finally assigning the parts as well as machines to respective cells as well as part families. So in the step 10, we are once again refining the part families as well as machine cells to get the final block diagonal form. So this is the proposed similarity coefficient in the iteration model. So this is similarity coefficient relation for machine cells, for machines, for finding for machines. Similarity coefficient of machines X and Y is equal to summation of J is equal to 1 to C, summation of process plan for X for parts X and Y up to P of the maximum of products, maximum of product of the manufacturing time ratio and the job sequence weight ratio of parts X and Y multiplied with the incidences AXJP and AYJP with the batch size PB of part J divided by summation of J is equal to 1 to C summation of P to P, the maximum of the product of manufacturing time ratio and the job sequence weight ratio and the incidence of part X, incidence of part J with the machine X, and the summation of the manufacturing time ratio of part Y into the job sequence weight ratio into the incidence of part J with machine Y into the batch size of part J, PBSJ. So here, I am using the values of manufacturing time as well as the process sequence weightage ratio. So here cycle time will be equal to summation of I is equal to M of manufacturing time plus waiting time plus setup time plus handling time. So here, the manufacturing time is considered as almost double the value of summation of waiting time and setup time and handling time. So the next I am including this process sequence weightage ratio. So this is calculated as the number of job minus the job sequence plus 1 divided by total number of operations of the particular part J. So likewise we are calculating similarity coefficient for parts of X and Y. So that is the summation of I is equal to 1 to M of maximum of the products, that is manufacturing time ratio into batch size ratio into the job sequence weightage ratio and the manufacturing time ratio of part Y into the batch size of part Y into the process sequence weightage ratio of the particular part Y multiplied with the incidences AXY and AYI divided by the summation of I is equal to 1 to M maximum of the products, so manufacturing time ratio into manufacturing time ratio and batch size ratio and the incidence AXI and the job sequence weightage ratio with the manufacturing time ratio of part Y into the batch size ratio of part Y into multiplied with the incidence of part Y and the job sequence weightage ratio of part Y, the machine I. So we are calculating the similarity coefficient values and forming similarity coefficient matrices of machines as well as components. So here by using this formula, we are finding out the row weight as well as column weight. So row weight, that is summation of y is equal to 1 to m similarity coefficient of the particular machines x and y into the arbitrary value x power m minus y for rows. So here for columns, so the similarity coefficient value multiplied with the arbitrary index power m minus x. So here arbitrary value x is considered as 1 or more than 1. So next we are finding out, we are doing the sorting of rows as well as rows weights as well as column weights. In the step 5 we are doing iteration. That is, we are repeating the step 3 and step 4. So finally in the step 6 we are identifying cells as well as part families from the unit diagonals in the instance in the matrices. Next in the weight based method, so in the step 7, so we are following this rule of thumb. So if number of parts is more than number of machines, so first we are doing the refining in the refining of part families. In the step 8 we are computing weights, that is weight is equal to x into pj of xk, where so pj of xk is equal to 1 by nj, that is so number of operation of the particular part divided by total number of operations. So in the step 9 we are assigning the particular component to the particular machine cell as well as particular machine to the particular family. Next in the step 9 we are finally getting the final block diagonal form by this refining, by this retrospective refining. So in the weight based method we are retrospectively refining the clusters to get the perfect clusters in the final block diagonal form. So this complete similarity coefficient is obtained from this simple similarity coefficient and this developed similarity coefficient. So earlier I have followed these two similarity coefficient relations, and finally I am proposing this complete similarity coefficient method. So this is the benchmark problem, 7 by 11. So 7 by 11, 7 machines and 11 components. So actually this is the actual data taken from the literature. So that is a root sheet or a process plan for these 11 parts. So we have this process plans. So I have simply converted this process plan into instance matrices 7 by 11 of 0 and 1, where operation is there, so the value will be 1, and along with that, so I am including the manufacturing time as well as job sequence. So here for the first part, so 1 and 2 operations are there, and so in the bracket I have given the manufacturing time also. So likewise I have taken all the values. So this part incidence matrix, by calculating similarity coefficient values, so we will be able to form these two similarity coefficient matrices, job matrix as well as machine matrices. Machine matrix 7 by 7 and job matrices 11 by 11. So next I am taking this machine similarity coefficient 7 by 7. I am calculating the row weights by using the formula similarity coefficient multiplied with the arbitrary index 2 to the power m minus y. So this is seventh so this is seventh machine. So that's why the value will be 0, power value will be 0. So likewise, I am calculating the row weights for all these machines. So likewise, so here I am calculating the column weights. So similarity coefficient of this particular machine multiplied with that is B8 multiplied with the arbitrary index to the power, that is m minus x. So 7 machines minus this 7th machine, so power value will be 0. So likewise, I am calculating weights for all the columns. Next, I am doing the iteration, that is I am sorting the row weights as well as column weights. So first I am arranging in ascending order for these row weights according to the row weights. Next, I am arranging the column weights in the ascending order. So now I am once again I am taking this similarity coefficient matrix to the second iteration. So now I am calculating a row weight as well as column weight. Now I am seeing, is there any perfect order or not. So there is no perfect order. So now I am doing this iteration, that is by I am sorting the row weights as well as column weights. So I am doing the same iteration process until there is the perfect order of row weights as well as column weights in the ascending order. So now in the fourth iteration, so I am getting the perfect order. So there is no change in the order of weight as well as order of weight in the rows as well as column. So now we will be able to identify the machine cells. So 5-1 first cell, next 6-2-3 second cell, and 4-7 third cell. So here we will be able to see the unit diagonals 1 and 1. So 1 1 1 as well as 1 and 1. So we will be able to identify the machine cell clusters in the fourth iteration. So likewise in the first iteration, likewise for the job similarity coefficient, that is for components. So 11 by 11 matrices, I am calculating row weights as well as column weights by using the relation, that is similarity coefficient value multiplied with arbitrary index to the power c minus x, c minus y. So likewise c minus x in the column. So I am doing the same iteration until the proper order of weights in the column as well as rows. So here, so in the seventh iteration, I am getting no change of weights of rows as well as columns. So here I will be able to find out the part families. So 1 5 9. So there is perfect unit diagonals formed here. So next, the second part family, so 6 8 10 11. So there is unit diagonals here. And the third part family, so 2 3 4 7. So there is also unit diagonals formed here. So in the fourth iteration, I am getting this block diagonals. So I am taking this pre-block diagonal form for calculating the weights, so in the weight based method. So for each of the parts, number of parts are more than number of machines. So I am finding out weights for each part, and in the respective cells, cell 1, cell 2, cell 3. For each of the parts, I am calculating the weights. So for the first part, so in the first cell, so it is having all the operations. So that's why I am assigning the weight 1. So likewise I am assigning weights to each of the parts. So in the eighth, for the eighth part, so so it is having so equivalentages in cell 1 as well as cell 3. So point 0.5, point 0.5. So likewise, I am assigning weights for all the parts in the respective cells. So finally, I am doing the assigning of part with the particular cell. So first part to the first cell. So it is having more weight in the cell 1. So likewise, I am assigning weights to all the cells. So for the part 8, so here, so it is having equal weightages. Arbitrarily I am assigning this 8th part to the cell 1. So likewise, so in the weight based method, retrospectively I am once again refining the clusters. So here, so this is final block diagonal form. So it is having 3 number of cells and 3 number of part families with the 2 exceptional elements. So we have got only 2 exceptional elements compared with so the pre block diagonal form. So here, so we have got nearly 4 exceptional elements. So number of exceptional elements are reduced after using the weight based method. So likewise, so we are doing this iteration process for all the benchmark problems. So this is first problem. So block diagonal form, which is having 4 number of exceptional elements, is reduced in this weight based method into 2 number of exceptional elements. So 3 clusters with 2 exceptional elements. And here this is benchmark problem, 6 machine 8 components problem. So part incidences are shown. So this is final block diagonal form, which is having 3 number of exceptional elements. And so the problem 3, so 10 machines and 10 components problem. So here, after using the weight based method, so number of exceptional elements are 5 and 3 clusters are formed. So in the problem 4, so we have got so 9 machines 10 components problem. So we have got exception elements are 5. So in the problem 5, 10 machines 7 components problem. So we have 2 alternative process plans for all the parts, for most of the parts except part 4. So here, so we are doing iterations for these 2 set of process plans, and finally, so we have find out the second process plan of all the parts are selected as feasible, and so we have got 2 clusters with nearly 6 number of exceptional elements. In the problem 6, so 5 machines 7 components problem. So we have got 2 clusters and 2 number of exceptional elements. So in the problem 7 machines 8 components problem. So we have got 2 clusters with 2 number of exceptional elements. So here cells are formed after 4 iterations and families are formed after 10 iterations. So in the problem 8, that is 8 machines 20 components problem. So we have got 3 clusters and exceptional elements are 11. So in the problem 9, 10 machines 8 components problem. So we have got 3 clusters with 4 number of exceptional elements. And in the problem 10 machines 12 components problem. So we have got 3 clusters and 4 number of exceptional elements. So simulations are carried out up to 27 iterations for machine cell and 9 iterations for part families. And in the 11th problem, 10 machines 20 components problem. So we have got 4 clusters we have got four perfect clusters, no EEs, and the problem 12, 18 machines and 24 problems. So we have got three clusters with the exception elements are so around 12, and the 13 problem. So we have got so four clusters with the considerable amount of E's. So this is summary. So we have got three clusters in the first problem. And so in the second problem, two clusters. So in all the problems, the exception elements are reduced considerably. So in the problem 12, so the exception elements are reduced from 88 to 40 to 19, as well as 74 to 25. So we have calculated performance criteria, that is machine utilization, grouping efficiency, as well as percentage of exception elements. Machine utilization and grouping efficiency proves the machine cells utilization, as well as the perfectness of clusters, as well as so if there is less or no number of exception elements, so then the clusters said to be perfect clusters. For 10 by 8 machines components model problem, so we have got machine utilization 96.3 and grouping efficiency 83, and the percentage of exception elements, that is 13. Actually we are trying to reduce the percentage of exception elements, and we want to increase machine utilization as well as grouping efficiency. So in these 13 problems, so we have almost for all the small size and medium size problems, so we have got good results through machine utilization as well as grouping efficiency. And for problem 3, 4 and 5, the grouping efficiency are more, and for the problem number 6, so the values are almost equal to the best known results. And for the problem 8, so we have got good results. We have got good results. 100 we have got 100% results compared to the best known results. And so for the problem 12 and 13, the larger size problems, so we have got considerably, so more than the average values compared to the best known results. So the problems 5, 6, 12 and 13 are solved with more than the average performance, with fulfilling the main objective of reducing EEs. So here from this performance evaluation, so graphs, so we can easily understand. So for small size and larger size, for small and medium size problems, the performance values are more than the expected values, as well as compared to the best known values. So here this proposed model can be able to give good results. And for the larger size problems also, this proposed algorithm can able to give more than the average performance compared to the best known values.